So welcome back. I'm going to cover section 2.5 in this video. So from previous lectures, we talked about the concept of a linear and doing sequences, if it's a linear sequence or this exponential sequence. And I kind of want to do a quick review. So if we take it and look at a sequence here, and I see if I subtract, I'm going to try a couple of things to see if I can predict what's going on. If I take this previous and subtract it, so if I just go 1030 minus 1000, I get $30. Okay, so this is 30. And if I do the same thing here, 1060 minus 1030, okay, well that's the same 30. 1090 minus 1060, yep, it looks like that's going to be 30. And then finally, if I do 1120 minus the previous of 1090, I again get 30. So I can kind of figure out this pattern of saying, well, it's just the previous plus 30. Okay. And if I can do that, if I'm starting at 0, I can write the linear equation for this thing. This is the difference between here. These were just ones. So for every time I increase 1, then I add 30 to it. So 130, 260, 390. Each time I get to 30. And then my starting point is 1000. When my x is equal to 0, I can just kind of write this off. So that's my prediction. So that in 10 years, I could say for year 10, after I start, then my value, my y value would be 30 times 10 plus 1000, and that would be 300 plus 1000, and then $1,300, okay? So I can use this to predict going down. Now here, if I subtract, if I start here, 1100 minus 1000, I get 100. This is 1100 minus 1000. But when I do this, 1210 minus 1100, I don't get 100. It's like 110. And then if I start doing this one, if I check 1331 minus 1210, it looks like I get 121. So this is not longer valid. Okay. So the next thing we wanted to check, well, is there some multiple in here that I can work with? So I'm going to take this and divide it by the previous. Well, I get 1.1 here, 3 zeros, divided by 1000. Each time I do a 10, I move my decimal place over. So I get that equal to 1.1. And how about if I do this, 1210 divided by 1100, grab my calculator over here and divide 1210 divided by 1100, and I see I get 1.1 again. How about this one? 1331 divided by 1210, 1331 divided by 1210 on my calculator. Again, I get 1.1. So it looks, I'm going to do one more, but it looks like we've got this constant division when we do this. So 1464 divided by 1331, and I'll run this last one out for us. And I get 1.0999, but it's approximately 1.1. I think this was like 0.1, but I just kind of rounded it off. Okay. So this looks good, and what I'm basically saying is that if I divide this by this, I'm getting 1.1. So each time I'm getting a multiple of 1.1. So this is starting times 1.1 times another 1.1 to get us this, times 1.1 to get us this, times 1.1 to get us this. And if I can do that, I can build this general model of an exponential. This is a linear, and this is an exponential. So for an exponential, I've got some initial amount, I'm going to call some initial, times some b number, some base number, to whatever power for whatever years we're doing. And in this case, this is the initial amount, and then this is the base. So what we've got for this model is that we're starting with 1,000. Each time we're multiplying times 1.1, and then that means multiply it that time. So if I wanted to know for x equal to 0, any number to the 0 power is 1. So this is just 1. I start with my 1,000. And then if I wanted to go for year, let's go year 3. Let's see if this works. Y is equal to 1,000. 1.1 cubed is just 1.1, 1.1, 1.1. And I'm going to go 1,000 times 1.1, and I'm going to find my exponent key and put that as a 3, and I get my 1331 as expected. And again, I can use this to predict for year 10, I would have that, and that would be that should be something like 2593.74. So if this was in money, $2,593.74. Okay. This is basically a 10% return on your money is what this is, 10% per year compounded each year. Okay, so we kind of looked at this quickly in the past when we were doing sequences, but this kind of helps us build the model. This is an exponential model. This is a linear model. And now let's kind of go through the slides and see what else we can kind of pick up on. Okay. Let me get over here, find my cursor, move this out of the way because it's always on top. And recall that exponential equations, this is an exponential equation, can be gross or decays. So actually I could have done this, and this is getting smaller and smaller, but when I do the division, it would still be the same number here. Okay, it would be this number would be different, but it would still be the same form as an exponential. Okay. So exponential equations change rapidly, not consistently. They in a patterned way, but they get faster and faster as we go forward. Okay. The part that makes the exponential function special is that the variable is in the exponent. And again, this is kind of missing the initial value that you're starting with, but that's okay. It's still, the main point is that it's the exponential with some base b. Okay. So here is the exponential equation format. Here's just a different kind of a different manner in which I did mine. But we're going to have some quantity, that's the Q, starts with some initial, this is Q sub 0, that's what that's read as, Q sub 0. And that's the initial amount at some times 0 is kind of what that 0 is saying at time 0. And then 1 plus or minus what you're either adding or decaying. So if you do 10% a year, this would be 1.1. If you decayed, so each year you're decreasing by 10% decreasing, this would be 1 minus 0.10. So you would have 90% of that previous year. And for this one, the 10%, each year you have 10% extra. So it would be 1.10 or 1.1. And then your T or your X has it, okay? So when we're evaluating, just like any other function in math, you can plug in values into X to solve for Y. For here, when we had the linear equation, this is kind of the same thing that I can still have a mixture here. So this one is kind of, here is some initial amount, and then I'm adding something over here. But, you know, as X is equal to different values, I can put these in here and do the full. Please excuse my dear Aunt Sally. The E is the X opponent, so you want to do things in the parentheses, like this 1 plus R first, and then you do the exponent, multiplication, division, and then your addition to get that answer. Okay. So this exponential tends to pop up a lot in different ways. when you have exponential growth, bacterial growth, when you put them in a nice medium, they tend to explode. That's the exponential growth. Decay, radioactive material tends to decay in this exponential fashion. They start out, get half of it more, and it kind of goes out, and you keep doing these half things. It starts out decaying pretty quick, and then it kind of goes down from there. Okay? So George Washington's wooden teeth are decaying rapidly. This amount is in grams, okay, is the weight of the tooth after T years and can be modeled by this function. Okay, so it apparently started out at 3.2 grams. For some reason they knew this, and then it decreases by 2% a year, so 98% of it is left. Decreases by 2%. A 1 here would always be 3.2. 1 to any number is just 1, so it would maintain that there. If this is less than 1, each time I'm multiplying it by a fractional, this is a decimal, but a fractional amount. Okay. So how much did George's teeth weigh after 225 years? So from the base year 0, when you started kind of keeping up with this thing, the base year 0 would be that base year 0, and then you go from there. So the amount that you would have, 3.2 times 0.98 T, you have 98% left. You're decaying by 2% a year. 100% is 1. 100 minus the 2% a year would give you that. Okay. So they're saying, what if T is 225 years? What's the weight? Okay. So your P would be 3.2 times, understood multiplication here in front of this parentheses, and this exponent is to the 225th. Okay. So on my calculator, if I grab this, I'm going to go 3.2, then my times, and then I want to go up here and I'm going to find my little X with a little box in it that says, you can put anything in there. Some of the calculators have a little caret that you can do to do the exponential, but here is times 0.98. And then I want to find my little box, and that goes up there, and then I'm going to do 2225. And that gives me that there's only going to be, if it's decaying at that rate, 0.034 grams. I'm going to round out to the milligrams. Okay. So consider this exponential decay function, and then it's just going to ask you certain things. What is the initial amount modeled by this function? 200. So we're starting out at 200. If x is 0, anything to the 0 is 1. And then that's just 200. So that's the initial amount. What is the decay rate? Well, it's decaying at a rate of 15.15, or 15% a year. Provide your solution in percentage form. And that's the 15. So here, if I go back, here is the exponential rate. That's the decay rate is the negative. So that would be decaying at a rate of 15%. What is the initial amount modeled by this function? 5. We start out with 5, and we're decaying at 0.03 or 3% per year, or whatever that time base is here, the x rate. So create an exponential function. Mr. John told his language arts class that each week students tend to forget 1/6 of the vocabulary words they learned the previous week. Each week is 1/6 of those. If the students learn 30 words, write an exponential equation to describe the number of words forgotten after 6 weeks. Okay. So this is saying So the number of words that they know starts out with 30 words, and the one would be 100%. But each year, each week, they have forgotten 1/6. So 6/6 minus 1/6. So this is the 1 minus the 1/6. So they would have 5/6, and then they would forget that, and then so they would have 5/6 left, 5/6 left, 5/6 left for each year, for each week. Okay. So they have forgotten 1/6. They know they're maintaining 5/6 of the previous ones. So this one would be at x equal to 0. They knew 30 words. At 1, after week 1, they would only know 5/6 of them. They have forgotten 1/6. And then again, they forget 1/6. They maintain 5/6 of that. And this looks like 30 times 5/6 times 5/6 times 5/6 ... for each week. Okay. So this is the general model. This is just 1 minus 1/6, and to give you that 5/6. Your family bought a house in 2002. Since that time, the value of the real estate in the neighborhood has declined 3% per year. If you initially paid $179,000 for their house, write an equation to model the value of a house after T years. Okay, so 2002, let's put up here, this is the base year. So for that, T is equal to 0, okay? And then the value of your house, it started out at $179,000. We can put dollars in here and the results would be. And then it is declining by 3%. So 1 minus the 0.03 to the T. So I have, if I lose 3%, I've got 97% of this still remaining. Did 97% of that, and then 97% of that. And then you don't want to leave it like this. You want to kind of simplify these things. So the value of the home would be 0.97 for T years. How much would your house be worth today? So today, this is 2021. I'm just going to go T is equal to 2021 minus 2002. We're going to say that's 19 years. So the value would be $179,000 if we keep our units. 0.97 to the 19th. And again, I'm going to run this on my calculator. .97, and then I find my exponential, and that's the 19. So that would be, the value of the house would only be $100,349.68. Okay. So one more, write an exponential function to model this situation, then find the value of the function after 5 years to the nearest whole number. A population of 290 animals that increases at an annual rate of 9%. So the R is a positive 9% annual rate. So this is really per year. That's all the annual rate means. And we start out with 2. So we want to say here's their amount or quantity, some initial amount. So we started out with 290 animals. and they're increasing at 9%. We don't want to mix numbers and percentages, so we need to convert that into a decimal, 0.09, and then t. So each year you're going to have 1.09 times the previous year. So you have the previous and then 0.09% that you're adding into that, and that gives you the original plus 9% of the original, and you just keep doing this out. So this is 290, 1.09 to the t in years. And then we want to know, find A where t is equal after t is equal to 5 years. So our population amount would be 290 times 1.09 to the 5th. So we're going to do this, and then here are just the calculator. It's going to work that out for you. 290 times 1.09 raised to the 5th. And we would end with 446.2009.2, and they said round to the nearest whole number. And then, so that would be just 446. Okay. So a house was purchased in 2012 for $150,000. If the value of the home increases by 3% each year, what will the house be worth in the year 2015? So 2012 is our base year, which means t is equal to 0 from that point, and this is when our model starts. Okay. So our house was purchased in $150,000. So the amount it's going to be worth is $150,000. It increases 3% per year. So this is 0.03, okay, that we're going to deal with. So it's 150,000, 1 plus 0.03 to the t, and I like to write this down as combining this plus your rate. And so this is for 2015. What is the house worth? In the year 2015, so I have to find out what t is going to be, and that's just going to be 2015 minus 2012. If this was 2012, I get 0. That's our base year, and then this is going to be 3. So that's what t we're going to use. That's by 3, 150,000, and that'll be 163,909.05 in dollars. So that's kind of the gist of what they want you to get out of section 2.5, and we'll look at some of those in class as well, and then move on to 2.6. So see you in class. Have a good day.